But Babak, I think you're muted. Oh.
Yes, sorry. Yeah, thank you. Good morning. So we want to continue the lesson today, but if you remember, there were some problems that was left over from the previous session. So let us finalize them. So first of all, we review a little bit, and then we go to the next lesson. Today's lesson is actually is a very simple lesson, important lesson, both of them. Yeah, but this is not exactly according to my taste, but I will follow exactly the book. So I think it's less confusing for you if I just follow exactly the book. So writing them. By the way, I am always writing what you're supposed to read, what you're supposed to solve on a school self in lektions planering or something like that. In the school self you will find. I always put the links to the videos and everything. So it's completely organized. You need to follow all those instructions. Okay. So let me solve these 5 problems which were left from the previous session, and then we go to today's lesson, which is quadratic equations, part 1, of course, graphical solution. So if you remember, there were 2 problems left for factorizing. So we are supposed to factorize these 2 polynomials. I don't know, have you already studied or thought about these problems or not? But can you just tell me, for example, for part K, do you have any idea what to do for this one? I want to factorize this expression, writing this polynomial as a product. Any idea what to do?
Maybe open up the brackets.
It might work. It might work. I don't know exactly. If you want, we can do that. But that's not a good idea, because opening up, first of all, you know that if you open these things up, it becomes more messier. Yes, it becomes bigger. My goal is not to simplify. My goal is to write it as a product.
Yeah, can I say?
Yes, of course.
Yes, you can see there's a squaring pattern you can see there.
Yes, that's a squaring pattern. Why? Of course, I have more than 3 terms involved, but this is written in a way that I can look at it as a sum or difference of 3 terms. So one term is this one. It's not completely one term, because if I open it up, it is 3 terms. But it is written in a way that I can see that at least I can see that this is one term, and this is the second term, and this is the third term. And then I have 2 of them complete squares. If I ask you what number is 2 power 2 becomes 9, of course it becomes 3. And then if I ask you what expression 2 power 2 becomes this expression, hopefully you can immediately say that this expression. If I raise this one to power 2, 2 to power 2 gives me 4, and this expression to power 2 gives me this. So this means that this is actually a squaring pattern. So if I realize that, then what I do for K is to write a pair of brackets and put a power 2 on top. And then I square this one, which becomes 2a plus b. Then I square this one, which becomes 3. But this is the negative version for a squaring pattern. So I put a negative sign in between. So that is this is the factorization of this one. But of course, nobody leaves in principle this expression like this, because this expression can be written in a more simplified form. I don't really need to keep these pair of brackets. So now I can multiply this inside. So this becomes 2a plus 2b minus 3 to the power of 2. And then I am done. Yes, because my goal was not to simplify this expression. My goal was to write this expression as a product. And of course, everyone sees that this is a product, because power 2 means this expression multiplied by itself. So that is indeed a product. So I succeeded. And this is clear that this cannot be factorized more. So this is the end of the problem. Any questions? Okay. So hopefully you now that your memory is a little bit refreshed, you can also immediately realize more or less the same idea is in the next problem. Yes? Can you see the pattern again?
Yes.
It's squaring pattern again.
Again, a squaring pattern, yes. I have 3 expressions. I can pretend that these are just one single terms. So I have 3, I would say, terms. 2 of them are complete squares. Okay, and by the way, I forgot to check that this is indeed, so I don't know why I forgot, because I probably knew that this is a squaring pattern. Even in this problem, I have to check, is it really squaring pattern or not? So let me just repeat it, sorry. So is it really squaring pattern? Yes, because if I take the square root of this one, it gives me this. If I take the square root of this one, it gives me this. And if I multiply these two and multiply it to myself, 2 times 2 is 4 times 3 is 12, so it becomes 12a plus b. This is the reason that it was indeed a squaring pattern. If it was just, I don't know, 11, so this is not working anymore. Okay, so that's good. Do you see the same thing here? Yes, because I have 3 terms involved, 2 of them are complete squares, but is it indeed a squaring pattern? I need to check. I take the square root of this one, it gives me x plus 2. I take the square root of this one, it gives me x minus 1, x minus y, and then I multiply them and multiply by an extra 2. Is this expression sitting in the middle? Yes. This means that this is indeed a squaring pattern. So that's also the same. So I would say that I open to a pair of brackets and I put the power 2 here. I take the square root of the first one, and then I have minus the square root of the second one. Okay, so even though this is correct, but this is not complete, not from factorization points of view, because whenever we can simplify things, we definitely simplify them. So this pair of brackets is unnecessary. I just remove it. There is nothing behind that. That means that that's a positive sign. But for the next pair of bracket, I have to be careful. This minus sign is not only for the first one, but also for the second one. So it gives me minus x plus y to the power of 2. Still, I can simplify it more, yes, because this minus y, this minus x, and this positive x are gone. So 2 and y are left. So what I do, I just write it as y plus 2 or 2 plus y, it doesn't matter, to the power of 2. And that is the factorization form of this expression. Any questions?
No.
No.
Okay. But do you remember there were 3 more problems left from simplifying things, if you remember? We learned about rational expressions. We learned how to simplify rational expressions. We need to factorize the numerator and the denominator and look for the highest common factors between these two. And then we are only allowed to cancel common factors, not summands, okay? So for example, if I want to solve this problem, I'm not allowed to simplify this x to the 3 with this x to the 3. It's not allowed because x3 is not, x to the 3 is not a factor of this expression. It's a summand, yes? Even though x to the 3 is a factor of this part, but still it's not a factor of the whole numerator. So I have to, this is, remember, this is the algorithm. You need to factorize the numerator. You can do factorization of the denominator in parallel. And when they are in finalized form, then you will find the common factors and simplify the common factors. This is the only thing that you can cancel from the numerator and the denominator, okay? So let us see how it works. Part G. So what is your suggestion for factoring the numerator? Any ideas? How should I factor the numerator?
I don't know if this is correct thing to do, but you can pull out like more, but I'd pull out just one x because so you can then remove.
But that's not a good idea. I'm not saying this is wrong, but if you just pull x out, then that is not fully factorized.
Yeah, but it helps because I can then use it to cancel out one x, or maybe that's not the right method.
No, this is a right method, but why? So it seems that you are solving the problem in more steps. I'm
Okay.
just telling you that it is not necessary to solve it in a step by step. So what I recommend, I will fully factorize the numerator. So instead of just pulling out 1x, what can I pull out?
6xy.
Yes, so I will pull out, I myself prefer to pull out 6xy, because otherwise I need to do it step by step, so several times. So why should I do that? So when I pull 6xy out, what is left from the first one is just x squared, and then what is left from the second one is minus 1. Okay, still I know that this is not fully factorized, but let me just do something for the denominator. You can go in parallel, or if you are not comfortable with this, you can just you can go to the margin. I don't know, you can just start solving the problem. You can write this and fully factorize that and put it in a box, and then go to the denominator, fully factorize it and put it in a box, and then bring it back to the main problem and then start solving. But I myself prefer to do it in parallel because it's not very complicated here. So what is your suggestion for the first step to factorize the denominator?
If you write it as x times x squared plus 2x plus 1,
Yeah.
that's how you can.
Yeah, exactly. So I pull out x squared, x out. And then, of course, you can, at this step, you can simplify these two. Why is that the case? Because if I ask you, is the numerator in the form of a product, you would say yes, because x is now a multiplicative. It's a factor, and x here in the denominator is also a factor, but this x is not a factor, okay? Even though you can just simplify right here, but let us not confuse. This is a little bit subjective. That's up to you. I prefer to fully factorize and then start simplification. From pedagogical point of view, it's easy. I think it's better. But of course, if you understand exactly what's going on, that's up to you. So what I'm trying to say is that if you at this stage simplify these two x, that's completely okay. But if you simplify these two x's, for example, here and here, that's not okay at all. Okay, so I just want you to have understand the difference between them. So is there any other way? Is there something that I can factorize in the numerator still? Yes, probably this is very familiar for you by now. This is the difference.
Conjugate.
Yeah, it's the difference of two complete squares. So I will put two pairs of brackets. I take the square root of the first one, x, put it in both of them, take the square root of the second one, which is 1. I put it in both of them. One of them positive, the other one is negative. And then in the denominator, still it's not complete. Do you see another pattern here? It's clear, yes? What's the pattern?
Squaring.
The squaring pattern, yes? And so this means it becomes x plus 1 to the 2. Why is that the case? Because I have 3 terms. 2 of them are complete squares. If I take the square root of this one, it gives me x. If I take the square root of this one, it gives me 1. If I multiply them and multiply them by 2, it becomes exactly the middle term. Now everything is in order, and then I can start simplification, yes? So if I ask you what are the factors of the numerator, you can say 6. Of course, if you want to say it in more detail, you can say 2 and 3, because the product is 6. And then I have x, then I have y, then I have x plus 1, then I have x minus 1. And if I ask you for the denominator, you would say I have x, I have 2 factors of x plus 1, because x plus 1 appears with power 2. Yeah. So here you see that there is one factor here in common. There is another factor here in common. So these two things are the only factors that can be canceled out from the numerator and the denominator, yes? So, and then what is left is this. I divide this numerator by this, and I will left with 1 here when I simplify. One of them is gone. And then here I can just take this power of 2 out, yes? Because I had 2 of them, one of them was gone, so one of them is left. And then if I want to simplify that, so what is for me, 6 is left, y is left. Of course, 1 I don't write, and then I have x minus 1. And then in the denominator, I have x plus 1, the only one which is left, so I don't really need to put a pair of brackets around it. You can stop here if you want, but sometimes people prefer to multiply it back, because when it is clear that nothing can be simplified, we can also write it as 6yx minus 6y divided by x plus 1. It doesn't matter if you stop here or here that I just wrote, so you can stop here. But the crucial thing is that don't be careful that you are not allowed to simplify these two things, because you see x appears as a summand of this as a factor. So x is not a factor, x plus 1 is a factor. Here x is not a factor, x minus 1 is a factor. And these two are completely different, so I cannot simplify anything. This is very important to recognize that when you can stop. Any questions regarding the solution of this problem?
No.
Good. So let us go to part H. This part H is also something I just wanted to let me put a star on it. I want you to pay attention to a point that this problem has. Yes? Okay, before reaching to this point, let us see why there is a point that is important to care in this problem. So I need to simplify a rational expression. The algorithm that I am using is to find the factors in the numerator and the denominator, and to see if there is a common factor so that I can cancel it out. So the first step is to factorize the numerator and the denominator. So can I factorize the numerator? It's clearly yes. What is the pattern? It's the difference of two complete squares. Okay, so let us do them in parallel. So I will draw a fraction line. In the numerator, I open two pair of brackets, take the square root of the first one, it becomes 3a. I put one here and one there. And then the square root of the second one is 2. I put one here and there. And then I choose one sign positive, one sign negative, or the other way around, of course. But what is your suggestion about factoring the denominator?
5a.
Yeah, we pull out 5a. Okay, this is the first thing that comes even to my mind. So I factor 5a out. Let us see what is the problem then. From the first one, 2 is left. And from the second one, minus 3a is left. Now, in this form, can I cancel this one with that one?
No.
No, because even though they are very similar, but they are not the same thing. Yes, 2 minus 3a and 3a minus 2 are different. Either I don't simplify these two at all and leave it like this, which is not, of course, a good idea, because if it's possible to simplify, it's better to simplify. So in this form, simplification is not possible. But if you learn this trick from the previous lessons and even from Math 1C, you know what to do, yes? It is not exactly like this in this form, but it is very similar. The only difference is that here I have 3a minus 2, here I have 2 minus 3a. Whenever this happens, that a minus b is there, but what you need is b minus a. I have repeated this several times. It's an important trick that you need to have in your mind, okay? Whenever I have a minus b, but what I need is the other way around, b minus a, you need to remember that you can pull out a minus sign, an overall minus sign out. So do you remember? A minus b and b minus a are not the same, but one of them is the negative of the other one. This is extremely important to remember. So it means that if you could foresee this from the beginning, I would take minus 5a out. But no problem, I couldn't recognize this matter from the beginning. Now I realize what the problem is. What I can do, for example, I can keep the numerator as it is. That's optional if you want to do something in the numerator or the denominator. But then instead of positive 5a, I write minus 5a. But instead of writing 2 minus 3a, now I am allowed to write 3a minus 2. Yes, so what I have done, 2 minus 3a is not equal to 3a minus 2. But according to the rule, they are negative of each other, yes? So instead of this one, I wrote minus 3a minus 2, But 5a multiplied by this negative, there is a multiplication going on. It becomes minus 5a, and the rest is there. And now if I ask you, what are the factors of the numerator? You would say 3a minus 2 and 3a plus 2 are the factors. If I ask you what are the factors of the denominator, you would say minus 5, a and 3a minus 2, and then you immediately see that this is a common factor, so it can be simplified. So then what I do, I divide the numerator and the denominator by this expression, so this becomes 1, and then I can simplify, this becomes 1, and then what is left for me is 3a plus 2, and I don't need to put a pair of brackets around that. There is no point for writing it anymore, and the denominator is minus 5a. Again, am I allowed to simplify these two a's? Yes or no?
No.
No, because even though a is a factor of the whole denominator, it's not a factor of the whole numerator. It's just a factor of one part of the numerator. But I myself prefer to put the negative sign in front of the fraction line, but that's completely optional. If you don't want to, you can just stop there. But I prefer to stop here. Okay, and then finally, the last problem. So the reason that I put this star here, because I want you to pay attention about sometimes it is important to factor a negative sign out. If I don't want to do that, then this expression will be left in this form. But of course, everybody agrees that this is a much more compact form of my expression. Whenever I can work with a smaller expression, it's always advantageous to do this. And now let us go to part I. So what can I do here? The algorithm is the same, by the way. So I go here. It's clear. What can I do for the numerator?
You can pull out y and x, I think.
Yes, exactly. And what is left? It's clear. This is x to the 4 minus y to the 4. But the denominator, I cannot do anything with. It's already in factorized form. Yes, it's a product. So I don't do anything with that unless one of these factors can be factorized more, but probably by experience you know that this is not possible. This is just, it is. But here, even though I have two complete squares, but this is not a conjugate pattern because the addition, I have the addition between these two. So that's not a conjugate pattern, but I don't need to be worried at all because it's already a product. So it is already in factorized form. Okay, so in this form, hopefully you see that nothing can be canceled out. But immediately I realized that in the numerator, I can continue to factorize, yes? So what I do, I would write x times y instead of x to the 4 minus y to the 4. I immediately realize this is the difference of two complete squares, yes? So I open two pairs of brackets, yes? The square root of the first one is x squared, so I put 1x squared here and 1 there. The square root of the second one is y squared, so I put y squared here and 1 there. I choose one of them positive and the other one negative. It doesn't matter which one is which. Okay, but still the numerator is not complete. Of course, here you immediately, can I simplify these two at this stage?
Yes.
Yes, because now all of them are factors, even though I prefer not to do it right now. That's completely subjective. So let me write, because the numerator can still continue. Because you see that this part is again a conjugate pattern, so I can factorize it, yes? So I can write it as x minus y times x plus y. What I have written here is the answer to this part. And then there is one thing left, so I copy and paste that one as well. And then in the denominator, I will have this expression. But now everything is ready. In the numerator, I have 1, 2, 3, 4, 5 factors. And in the denominator, I have only 2 factors. But both of them are in common. Do you agree? You see that x plus y repeats itself here. X squared plus y squared repeats itself here. So these are common factors, so I can cancel them out. So this and this are gone. So 1 and 1 is left instead of them. This one and that one are gone. So 1 and 1 is left. So if I continue in the numerator, I will have xy times x minus y. In the denominator, I will have just 1 times 1. But nobody writes 1 times 1 or division by 1. So the answer is just simply x times y, x minus y. If you want, you can stop here. But now that we know that this is not being simplified anymore, so I can multiply it back, it becomes x squared y minus xy squared. This is optional. If you want, you can stop here or you can stop there. Okay, so hopefully this was a good recap of what we have learned so far. This is extremely important lesson. So next year in Math 3C, the first chapter actually deals with these kind of expressions. Then there you will learn how to multiply, add, subtract, and divide rational expressions. Okay, but this is crucial to not to forget about this lesson. Until the next year, of course, I will repeat and recap you again. But this is I just want to mention that this is a very important lesson. Okay, so now I want to start today's lesson. Quadratic equations, part 1, graphical solution. Okay. So what do we mean by quadratic equation? Yes. Let me define it for you here. Definition. An equation of the form ax squared plus b times x plus c equals to 0 is called a quadratic or a second degree equation. So let me make it more complete. It's called a second degree equation, but let me emphasize here. If A, B, and C are real numbers, and A is not equal to 0. Okay, so quadratic or second degree refers to this second power. Okay, so if you have an equation in which you have the second power of your unknown, that is called a quadratic equation or a second degree equation. So these are the coefficients. These numbers that you see here are called the coefficients of the second degree equation. And the reason, yes?
Does that mean that a third degree equation has ax3?
Yes,
so
yes.
ax to the power 3. Okay.
Yeah, exactly. Yeah. So the degree of an equation refers to the highest power of the unknown that appears in your equation. Yes? That is the degree of an equation. And the reason, why do you think that we emphasize that A is not equal to 0? You see the point?
Because then it wouldn't be a quadratic or second degree equation.
Yes, so exactly. If A is equal to 0, this term will go away, and then I will face with a first degree equation. But first degree equation is what we learned and studied quite extensively in Math 1C. So the reason that I am assuming that a is not equal to 0, because if a is equal to 0, this is not a quadratic equation anymore. My goal is to study just quadratic equations. So this, I emphasize that a shouldn't be 0, even though b and c can be both or one of them be equal to 0. But I'm not allowed to put a equal to 0 if I am going to study second degree equations. Okay. For example, by the way, this is also a standard one. There is no guarantee. This is in an organized way. Usually in first degree equations, if you remember, we could have a mess between unknowns and numbers on different sides, yes? And then we learned that for solving them, we move everything containing the unknown to the left by considering the change of signs from positive to negative, from negative to positive. And I will move the constant numbers to the right with the same method. And then finally simplify and then divide what is on the right-hand side by the coefficient of the unknown. The reason, so it was possible to solve that equation in that way. But when it comes to the second degree equation, we want later, when we continue, we want to find a formula for the answers of this equation. Either you memorize that or you have it in your formula sheet. You use that formula always to find your solutions most of the time. There are other methods as well, but that is the most common method. That formula works only if you write your second degree equation in this standard form. It means that for being able to use that formula, you have to move everything to the left-hand side, for example, so that the right-hand side becomes equal to 0, and then you're allowed to use the formula. So this is why from now on, when I'm talking about the second degree equation in a standard form, I mean this, so that the right-hand side is 0. Okay? Example, I would say that all of the following equations, are quadratic equations. Yes? So for example, number 1, I can say 5x to the 2 plus 3x minus 8 equals to 0. Okay, so that's a second degree equation. If I ask you, if you compare this one with this one, that's exactly in the standard form. If I ask you what is the value of A, you would say it's 5. What is the value of B? You would say it is 3. And if I ask you what's the value of C, you would say it's minus 8. So these are the numbers. Okay, so that's one quadratic equation. Might be, if I want to give you the simplest possible quadratic equation, I don't know if you agree with me, but I can write this. X to the 2 might be equal to 0. This is also a second degree equation. It's probably the simplest possible second degree equation, which of course you really don't need any extra knowledge to answer what are the solutions to this, because you know that there is only one solution for this different equation, and that is x equal to 0. So it doesn't mean, so here, even if you haven't studied this second degree equation systematically, you still can solve some of them. Yes, this is one of those special cases that you can immediately solve and find a solution, which is x equal to 0. Yes, but if I ask you what is a in this problem, you say that a is the coefficient of the quadratic term, so a is 1. If I ask you what is b and what is c, what are your answers about these two, b and c?
C would be 0.
B is also 1.
No,
Jag
b is
pratar
not
med bara.
1. Why do you say b is 1? B is also 0. Let me tell you, what is a in the standard one? A is the coefficient of x squared. Hopefully for every one of you, it's clear that this is 1 because we haven't written anything. Another name for x squared is just 1x squared. But what is b? B is the number which is multiplied by x. But in this equation, you don't see any x. Why? Because its coefficient is 0, so that 0 times x is 0, and the people doesn't write 0.
Right.
So b is also 0, and c is also 0. Yes, is that clear for everyone? So when I write x squared equal to 0, if I want to recognize a, b, and c as in the standard equation, everybody should answer this. A is 1, b is 0, c is also 0. Is that understandable for everyone?
Yes.
Yes.
Okay, good. And then let me just give you some, because now I think everyone knows what's going on. So for example, number 3, if I write x squared plus 2x is equal to 3. Yes. What do you think? Do you think this is also a quadratic equation?
I guess so.
Yeah.
Yeah, that's also a quadratic equation, but it is not written in a standard form. Yes.
Wait, Babak, the question, the example says that all the questions are quadratic
Yeah,
equations.
yes.
So obviously it would be.
Yeah, that's clear. But I really want you to understand, this is a quadratic equation. If someone asks you why, because you say that my unknown is x, and the highest exponent for my unknown, here the exponent of my unknown is 1, and here is the exponent of my unknown is 2. So the reason that the highest exponent for my unknown is 2 is the reason that I call this equation a second degree equation or a quadratic equation. But is this written in a standard form? You would say no, because on the right hand side I see 3. So if I want to ask you what is A, what is B, and what is C, it means that I need to find the standard form. This is not part of this question, but I can write it here. So you can change it into a standard form. How? You keep everything containing x and everything, you move everything to the left. X squared plus 2x is already on the left, so I move 3 to the left, but I need to respect the rule of changing the sign. So positive 3 becomes negative 3, and when I move it, nothing is left on the right hand side. So then it means that I can write A, B, and C. Now, can you tell me what are these numbers now?
A is 1, B is 2, and C is negative 3.
Exactly. So this is very simple. So as soon as you see x squared in your equation, you realize this is a second degree equation. You need to learn what I am going to teach you in several sessions, and then you need to learn how to solve this equation. Okay? But today we want to just talk about, I'm just following exactly the book, so this is on page 15. We will continue today until page 18. So of course page 18 is in exercises. So the first thing that we want to learn is how to solve this equation graphically. So assume that you have a graphical tool available, like your calculator or Geogebra or any other means. So then you can use that, solve your equation graphically. Okay, so how should we do that? Before doing that, I want to recall a little bit about functions that we learned about on in Math 1C, okay? So functions recall, yes? Especially, I want to talk about that part of the function which is related to the graph of a function, yes? So remember that when we are dealing with a function, so for example, I have y equals to f of x, and then if I can draw a graph representing this function, yes? So for example, assume that this is the coordinate system, and then I have the graph of my function. So let me try to draw one random shape here. So for example, like this, okay? So this is the graph of my function. And now I tell you, for example, this point, for example, let me consider that this point is, let me change the color so that you are not confused. So assume that the value of this is A. Okay. One thing that I might ask you is that, what is f of A? So you see, usually when I talk about a function in mathematics, it means that I give you the rule. For example, I tell you that f of x is equal to x to the 3 minus 2x plus 1. This is the rule for my function. And then you can draw the graph of the function. Not easily, you need to wait until Math 3C and Math 4 to learn how to draw the qualitative form of a reasonably precise graph of a function. But assume that you can draw the graph, or the other way around. The graph is given to you instead of the rule. And now you need to know how to answer some questions. The first question is that I ask you the value of the function at different values. Yes. So I want to answer this question. Do you remember what is the strategy? So how do you understand what is f of A by this graph? How should I do?
So you put like a meat mincer thing. So like you said, you have like f is the machine. You put a number there or something that's A, and it gives an output.
Okay, but how? If I want to specify the exact output using this purple graph of the function, how should I do that?
Well,
Just explain me what is the method. So for example, this is assume that this is a real graph of some function which I don't know, and this is some number A, and I am asking you, of course A might be 1 here in this picture, but I don't want to work with numbers because it becomes hard. Assume that this is a given number and I ask you what is f of A. How do you do? How do you graphically answer?
Yeah, the answer is is on the y-axis.
Yes,
Like
and
it's
how should I
corresponding.
find that particular point?
Well, you look at A and then you like, I don't know, use your finger or something, or look up and see where where the line intersects.
Exactly. Yeah, that's the problem. That's the procedure. Yes, what you need. Exactly. I wanted you to explain this. If I want to answer f of A, what should I do? I will go up or down in a direction. If I go down, there is no hope that I intersect the graph. So I will start going up and down. I choose which one I will intersect the graph. So I will go in that direction. Okay. So I will go up so that I intersect with the graph. And when I found that point, I then go horizontally to intersect the y-axis. If this point is, whatever this point is, I don't know, here, for example, in my picture, it's a little bit lower than 2 or whatever. Let me call it, for example, capital A. Then, instead of this question mark, I would write capital A. So this is the way that I find the value of a function using the graph of the function. Is that clear? Yes? For example, let me give you another one. For example, what is f of b? I am asking you, what is f of b? I will do the same thing. I need to draw a vertical line so that this vertical line intersects the graph of my function. Of course, it's clear in this picture there is no hope if I go up. There is no intersection happening. But then I will go down, then I will get an intersection, then I will go horizontally so that I intersect the y-axis. Then this value, assume that this is capital A, B, is the answer that I have to write here. Yes? So let me just do this here again. So I will go down, I will find the intersection point, I go horizontally, and then I get a point here, capital B. So the answer to this question mark is capital B. Is that understandable? So let us answer these questions. Is A positive or negative, this capital A?
Positive.
positive, but it is clear that this capital B is negative. So the
Yes.
value of the function at A is a positive number. The value of the same function at a different point turns out to be a negative number in this case. Okay, so this is something that you need to know. A graph of a function is given, and then I choose a number in the domain of my function, and I ask you what is the value of the function on that number. So you start with that number, you see in which direction, if I go vertically, I will intersect the graph. I choose that direction and go on so that I intersect the graph, then I start moving horizontally, yes? And then that number that I get on the y-axis is the value of my function at that point. Let me just make this a little bit, because this is very important. This is not, by the way, this is not for the quadratic functions. This is for all, this is completely generic. I'm just talking about all possible functions. This method will work. So for example, if I give you this as a point and I ask you the same question, what is f of c? Then you do the same thing. I go vertically. There is no point to go vertically downward, so I will start going vertically upwards. So then I will get this. But then I start going horizontally. Of course, in this case, if I go horizontally in this direction, I will not find the intersection with the y-axis. So it becomes clear that I need to go horizontally here. And then when I get this point, let me call it capital C, then the answer to this question mark is capital C. So I think it's very, very easy. It's very easy. But you need to also, but this is what is important in this lesson is the other way around. A point on the y-axis is given. So in principle, now the answer is given. This number is wanted. So there are two types of questions. The graph is given, the number is given, the value is wanted. Another type of questions that is more important here is that the function is, the graph of the function is given, the output of the function is also given, the input or inputs of that value, the input values or values are wanted. Okay. For finding the value, you are not confused. You will always get one single value. But the other way around, you might get one, you might get none, or you might get more values. Okay. So now let me change my color so that I want you to see how we do this. For example, let me go and do this. I'm asking you f of x is equal to, say, d, and I am asking you what is x. Okay, of course, this is very vague idea, but assume that d is here. So let me just tell you where d is. So assume that d is somewhere here. This is capital D. Yeah, let me, by the way, this is not a very good picture. Yeah, that is not a good starting point. So let me write this one. So this is D. I'm asking you, do you feel the question is different? Here, the question mark is in for the output, yes? But here, the question mark is for the input. I am asking which value or values, if they exist, satisfy this property so that f of x becomes equal to d. So it means that I need to find a point here somewhere so that when I calculate f of that point, it becomes d. Yes, for example, is this an answer? No, because if I go vertically up and go here, then this intersection point is not this one. Yes, it is not this one. So this point is not the point. Is this the point? No, if I go up and then go here, I get this one. This one is still not this one. But I cannot still start trying all these things because there are infinitely many. What is the more practical way of understanding that value of x, instead of checking these things one by one to see which one works, which one does not work?
To start with D, you go from
Yes.
D to the y equals fx.
Horizontally, I go to the D, I start
Exactly.
from D, go horizontally in a way that I can have an intersection, then I go vertically. Yes, the other way around. Exactly, thank you. So what I do, I will go horizontally in a way that I will have intersection. So this is possible, this is intersection. Then I go vertically. And when I do that, assume that this number is M. Now you will see that this M is, this question mark is M. But something that you need to be careful here is that it might happen that you can do, you can find more than one answer. Yes. For example, if I give this point to you, let me just do this. If I give you this point here, and I ask you the same question, I am asking you what is that value x so that the answer is E. The method is the same, so I will do the same method. I will go horizontally in a way that I have the intersection. But now you see that I have two intersections here and there. So let me just do that. So I will go in this direction here. Yes. And then I will have two intersection points here and there. And then I go vertically. So this point and this point are the two answers to this. Here, there is no one single answer. There are two answers. Yes. So I don't know. For example, let me call one of them M, N, and the other one, for example, P. So then I would say that this X is either N or X is equal to P. Yeah. Is that understandable?
Yes.
Okay, now let me ask you the same question, but give you a little bit concrete number. So I'm asking you in the following, in the graph, in this graph, for this function, how many solutions are there for f of x equals to a particular number 0? How many solutions do you think there are?
One.
No. You see here, no. So I don't know why you are confused. So if this
Oh
is
wait, I misunderstood the question.
yeah, so let me just explain again. So this, if I ask you what is the answer for f of x equal to E, you are supposed to find E on the y-axis.
Yeah, I thought of doing the opposite, finding like y. Well, yeah, I was
Yeah,
thinking
okay.
if P was E.
Okay. So then you go horizontally so that you find the intersection points, and then go vertically so that you find the intersection points on the x-axis. Now I am asking you the same question, but instead of choosing a particular E, I am choosing E to be equal to 0. But can you just tell me, I will do the same thing, yes?
There are two.
There are two, yes. I need to
Yes.
find 0 on the y-axis. This is my y-axis. I find 0 of the y-axis, which is this one. From this point, I need to go horizontally to find the intersection points. But the intersection points are these two, and I am supposed to go vertically to intersect the x-axis, but this is already the intersection with the x-axis, so I don't need to do it the extra. So let me just repeat. For E, I went horizontally, I found the intersection points, then I went vertically to be able to find the intersection point with the x-axis. But this is a little bit exceptional. It's even easier. I start, instead of starting from E on the y-axis, I start from the 0 on the y-axis, which is exactly this point. Again, I go horizontally so that I can find all intersections with the graph. It is clear that in this picture, I have only 2 intersection points. One of them is here and one of them is there. And then the next step was to go vertically to find the intersection of this line with the x-axis, but this is already done in this case. So the third step is already done. So I would say that these are the answers. So if I give you these numbers a name, so let me call this point, for example, S, and let me call this point T, then you would say that to answer to this would be there are 2 solutions. And if I ask you what are the solutions, you say that one of them x is equal to S and the other one is x equal to T. So is that clear?
Yeah, one question.
Yes.
So how do you know that the line isn't gonna like further away, like it's gonna go down and create
That's a good
another
question.
intersection?
No, that's a good question. If you want to talk about exam problems, you need to be careful that when I stop here, it means that I am telling you that this will continue like that forever. Okay.
Okay.
Babak, I
But
have a
of course,
question.
this question is completely clear. You are saying that how should I know that this is not coming back? Yes, of course, you are right. If it is coming back, I will have another root here as well. Yes. So this is actually crucial. If you draw the graph of the function, by the way, that's a good question. This is why just having a very advanced tool is not important. You cannot just use an advanced tool to solve the problem. You really need to understand mathematics. You are right, because even if you have GeoGebra, you draw the graph of the function, your display, your monitor is limited. So how do you really know that this is not going to happen, that you have another intersection point further away, which is not clear in your monitor right now? Yes, these are good questions.
Babak, I have a question.
Yes?
Is the amount of possible answers equal to the degree of the equation? Because we're solving second degree now, and every single time, like it's been the highest
Yes.
number
No,
happened to.
that's a good question. This turns out to be, it's called fundamental theorem in algebra. And this means that if I am facing a quadratic equation, it is not guaranteed that I have 2 roots. Yes, when I have a 1 degree first degree equation, in a not very if it is not a very special case, it's always guaranteed to have 1 single solution. But when we go to higher degrees, what we can say is not this statement. This statement is not in general true, to say that because this is second degree, I have 2 roots. No. What you can say is this: because this is second degree, you have at most 2 roots. It means that it is possible that there is no solution at all. And then I can, of course, these are not very hard things to understand. You can immediately understand that. So here, if I ask you how many solutions are there for this quadratic equation? How many solutions are there? I'm always working in real numbers. In case you know a little bit about complex numbers, forget about that. I'm just working in real numbers. So how many, is this a quadratic equation? The answer is yes, because this power is 2. But how many solutions are there for this equation? Nothing. Because there is no number so that when I raise it to power 2, it becomes a negative number. Even if the number that you start with is a negative number, its second power is still not positive, yes? So this can happen. This equation that I mentioned, how many solutions are there for this equation? We saw that there is only 1 single answer to this equation, and that is exactly 0. But if I ask you how many solutions you see for this quadratic equation, immediately you realize that there are 2, positive 1 and negative 1. And then there is a theorem in fundamental algebra tells you that if you have an equation of degree n, the number of solutions to that equation is at most n. For example, if I have a 5th degree equation, it might happen that this equation doesn't have any solution at all, or it might have one single solution, two solutions, 3 solutions, 4 solutions, or at most 5 solutions. How this will behave depends to the detail of the function, of the equation. So what you need to be concerned about is only 2nd degree equations, and you need to know that there are 3 possibilities. We will come to these later, okay? I don't know, did I answer your question?
Yes.
Okay, good. So did I also answer your question, Rocco?
My question?
Yes, you said that how should we know that this will not go back?
Yeah.
Okay. In the exam, if I draw something like this, it means that this is going to continue like this, okay? I will not make you be confused.
Okay, yeah.
Babak,
Yes?
what does these functions have to do with quadratic equations, really?
No, this function doesn't have anything to do with quadratic functions, but we will see that quadratic functions, the graph of the quadratic functions, are only of this type or of this type.
Okay.
So there is only one single turning point for quadratic functions. Here you see that I have several turning points. Yes, this is definitely not a quadratic polynomial. It's different. But here, I just want to tell you, I want you to, because in the book, they are only talking about these graphs, but I'm just telling you that these are completely generic. This is very, very important to know. Whenever you are dealing with a function and its graph, you really need to understand what's going on. So you need to be able to answer this question in this direction and the reverse direction, not only for quadratic polynomials, but for all sorts of functions. But of course, as Gustav mentioned, we only want to talk about quadratic equations. So I think it's very, very clear now what to do, yes? So let me write this as a remark. I want you to help me to write this remark, okay? So this is what I want you to know. From all this discussion, I want you to understand this. Can you tell me what to do? I would write you complete the sentence. To solve the equation f of x equals to 0 graphically, so can you tell me what to do? Assume that you have some tool in your hand that you can draw the graph of any function. To solve this equation of your function equal to 0 graphically, what you do?
Does writing it in your calculator count as a step, or do we
Yes.
already assume that's done?
No, just tell me. Yes, you first use your tool to draw the graph, and then?
Exactly.
And then?
Then you would look, you would find the value, which in this case is 0, on the graph.
No, make this part simpler. So, okay, then?
And then find the intersections horizontally.
The intersection with the x-axis, yes.
Yes.
So to solve the equation graphically, we draw the graph. We draw the graph, locate the intersection points of the graph with the x-axis, and read the x coordinates of the intersection points. These x coordinates are the solutions or roots. Solutions in equations are sometimes called roots or roots. I think in Swedish it is written in the book noll ställe. Yes, something like this. The solutions or roots of this equation. Okay. So it was very important to understand this remark. The way that I explained is I wanted you to understand this remark, but of course, when in practice, you just need to use it. Draw the graph of your function and locate the intersection points of the graph of the function with the x-axis, and then read the x-coordinates of those points of intersection. Those x-coordinates are the solutions or the roots of the equation f of x equal to 0. And then let me, by the way, let me change the color of this 0, so making it important. So this number should be 0, okay? Okay, so the only thing that I want to do now is just...
Babak,
yes, yes.
could I just finish writing that down?
Yes, of course.
Thank you.
Okay. Now, I think it's better to do it using GeoGebra. If I can share my screen with you and somehow that you can also see the GeoGebra screen, it would be better because it's very hard to draw these things by hand, okay? So I don't know how to write it. So it's better to write this here. You can write it on a piece of paper. So when I go to the GeoGebra screen, I don't need to go back and forth to make you dizzy by looking at your monitor, okay? So example, solve the following equations graphically. By the way, this method is not only for the second degree equation. So remember, for some reason, if you need to solve a higher degree equation, even more than quadratic ones, so now you know how to do graphically. You just draw the graph of the function and find the intersection points of the graph of the function with the x-axis and read the x-coordinates. So this is completely generic, but solving higher degree equations using analytical methods is extremely hard and sometimes impossible. Okay, so this I want you to know. But still, you have a very good method in your hand to solve all possible equations equal to 0. Okay, solve the following equations graphically. Like, of course, let me just give you some examples from the quadratic one. So number 1, so let us solve this equation. For example, I would say x squared plus 2x minus 3 is equal to 0. So please write them down in a piece of paper, so I will not probably refer that much to my iPad screen. So the other one is, for example,
it minus 3?
Yes, minus 3.
Okay.
And then I will have, for example, this equation, x squared plus 2x plus 3 equals to 0. And then let me give you another one. So these are 3 possible cases that can happen for a quadratic equation. And let me write this one as well. So I will have x squared plus 2x plus 1 equals to 0. Okay, so these are the equations that I want to solve using graphical tool. Okay, so let me pause this video. Okay, now we want to solve those equations that I mentioned graphically. So let me just open this x-axis. So let me see. My numbers are not that good. So let me go in. Okay, now, yeah, I think it's better now. So this is my coordinate axes. And then, do you remember? So the first equation was, let me just type it here for you. So it was x to the 2. And then I have plus 2x. Oops, it goes down, sorry. I need to go down. And then I have 2x. And then I have minus 3. Okay? Of course, in principle, GeoGebra knows whenever you put something here, it starts automatically drawing. But in principle, you need to write y equals to this one. So that's my function. Okay? So it's I want to find the answers to this. Let me change the color here so that it's more clear. So how should I do this? So color, for example, let me choose red. Okay, so that's better. And now if I ask you, so what I have done, I have drawn the graph of this function. According to GeoGebra, the graph of this function you see is this one. And then what I need to do, I need to find the intersection points of this graph with the x-axis and read the x-coordinates, okay? So if you want to, I think, let us see if it works in that way. I go here, this is intersect, you see. I choose intersect here, this is now working intersect. So let us see if it works here. I highlight this and I highlight the x-axis. Yes, but the points are so small that might be you don't see them. Let me increase the size here and let me fill it in. Okay, so now you see that these 2 points is the intersection of this function with the x-axis, and it is super simple to read these numbers here. Of course, these numbers, if are not passing exactly through the grids, it's not easy for our eyes to read them, but in GeoGebra, you can usually immediately find them to any desired accuracy, okay? So here, if I ask you how many roots, how many solutions does that equation have? You say immediately 2. And if I ask you, do you know the numbers? Do you know the solutions? You would say yes. One of them is 1. The other one is minus 3. What does it mean? It means that if you choose 1 and put it instead of x, it becomes 0. You can check. 1 to the 2 is 1. 2 times 1 is 2. Added to this 1 is 3. Minus 3 is 0. If I choose minus 3 and here, minus 3 to the 2 is positive 9. Positive 9. 2 times minus 3 is minus 6. Positive 9 minus 6 is 3. 3 minus 3 is 0. So you see that these are the solutions. And of course, I have good reason that this graph will never turn back. We will discuss about these things. Here, if you don't have that math knowledge, at the moment, you are not 100% convinced that these are the solutions, because that is the question Rocco asked. It might happen that this graph will go out, I don't know, out of my monitor and go back to the x-axis again when it is not clear here. But at least I can convince myself by zooming in, zooming in, zooming in, zooming in, and see that this is not happening. But you know that how many times I zoom in, it is not still guaranteed that this is not going to happen unless I have a very good reason. And that reason is not based on computer, it's based on your mathematics knowledge. So this is why I'm saying that even if you have a best computer, you will not be independent of math knowledge. So these computers, by the way, these algorithms knows about a lot. The people who put these programs, they actually develop these codes for these programs. They actually using math knowledge. So this is why they are so good in capturing the essence of what we want to do. Okay. So let me go back here. So that, okay, so I hope that you see that this lesson, even though it's very important, but it is very, very simple. Okay, and let me just do the other one. So let me delete this. Where is that? Deleting it, yes. And then if you remember, the other equation was y equals to what? It is x to the 2 and plus 2x, and then I have this time positive 3, if I remember correctly. Yes, that's positive 3. And if I draw the graph is this. Let me change the color here as well. I don't know why this turned into black. Okay, this is better. Okay, now can you tell me, based on this graph, how many solutions do you predict for this equation equal to 0? By the way, don't get confused. I am drawing a graph of a function. Using the graph of the function, I am solving this equation equal to 0. Okay, be careful about that. Okay, so what is your guess? By looking at the graph of this function, assume that the behavior of the function is exactly what you see in the picture, and nothing special will happen when you go outside your display. So based on this information, how many solutions do you predict for this equation equal to 0?
0.
Nothing. Yes, why? Because you see there is no intersection point between this red graph and the x-axis. So we will see later how analytically we can come to this conclusion that there is no solutions for this equation. But for the time being, I just want you to understand, because there is no intersection between the graph of this function with the x-axis, there are no solutions at all. So the answer to the second part is that no solutions. I don't want to go back to my iPad screen because I have to stop sharing, open the sharing, and then when I want to come back, I have to do the same thing. Okay. Any questions here? Okay,
No.
now let me any questions? No?
No.
So let me delete this and then go to the other equation, which was x to the 2. So let me write y. In principle, I should write y equals to, and then x squared plus 2x plus 1. Yes. And then if I change the color again to something better, green. Okay, so this one. So how many solutions do you predict for this equation equal to 0?
One.
One.
Just one. And what that number is?
I guess it's -1.
It's -1. So here, the x-axis actually just touches the graph at one point. So if I go to intersection point again, you see, I choose this one and this one. There is only one intersection point, this black dot here. And then I read the x coordinate. You see, this is the point A, and the GeoGebra tells you that the coordinates of that point is -1 and 0, and I am only caring about the x coordinate, so it's -1. Yes. Okay, and then of course you can just I want to you to see that this is also possible if we have very strange equations. So for example, I can write, by the way, if some part of the equation, for example, let me write in GeoGebra at least one. So forget about the drawing. Don't look at the drawing. See, concentrate on what I am typing. For example, if I want to solve this equation plus, so let me write 0.2, and then I go here, and then I write +5, and then I would write equal, and then I would say, for example, 4x, yes? So you see, I don't know, this GeoGebra is confused. Do you think that this should be confused or not, first of all?
Well, what it's showing is that there's one solution.
No. Be careful, Rocco. This is the wrong I would say that this is confused, actually. The reason is that if I ask you, is this a graph or not? Is this a function or not? What do you say?
I say no.
Equation.
Well, you only have value
Yes,
for
exactly.
x.
So this is why GeoGebra doesn't know what to do, because I am not following the rules. This is not a function. only the graph makes sense only if I have a function. Here I don't have any function, I have equality. When I have equality, that's an equation. I can ask GeoGebra maybe solve this equation. Okay, let us check if it works or not. Solve, you see, yes, there is another one to solve this, and instead of that equation, let me see if I can copy and paste this one inside. Okay, and let me write it here. Okay, and you see now GeoGebra is not confused. This graph is deleted and two numbers appear here as the solution, because now I am choosing the right syntax, I'm choosing the right command. I am asking GeoGebra not to draw the graph. This is meaningless. I want you to understand. This is an equation, not a function. So I'm not allowed to ask, draw the graph of that function, because that's not a function in the first place. But I can ask GeoGebra to solve this equation for me, and GeoGebra provides me with two exact values, minus 5 square root of 3 plus 10, and x equals to 5 square root of 3 plus 10. Let us investigate this a little bit. Now, instead of solving it, now assume that you want to solve it graphically. Can you tell me how to do it? Because this is the only way that we
Put in y equals and the entire equation.
Can you tell me what, that's my point. What is the entire equation?
Can I say?
Yes, yes.
Yeah, so I think you'd start off by moving 4x to the other side, so you have 0, and then you can do it.
This is crucial, because the method that I wrote in the remark, if you remember, I wrote the right-hand side 0 with red. This method only works if it is in red, okay? I don't know why GeoGebra did this. Okay, so let me just write this one. Y equals to, so be careful. If you have an equation, can you see this when I move this cursor? Yes, it is bigger now. If you have this equation, on the right-hand side, you don't have 0, and you want to solve it graphically, first what you need to do is to move this to the left-hand side, and then write y equals to 0.2 x squared, yes, and then minus 4x, because I moved 4x to the left, and then plus 5. Again, do I put equal to 0? No, because I am asking GeoGebra to draw the graph of this function. And by the way, what you see on my display, if I don't know mathematics, I might be fooled by this graph, and I see that this is more or less a straight line. But because I know mathematics, I am definitely sure that this cannot be a straight line, and I know what is the shape of this graph, so there should be a turning point, which is not here. So this motivates me to zoom in or zoom out appropriately to see the entire picture. So by the way, let me change the color here as well to make it more clear. So this red one, you see, of course it is clear. You see below, you can see it's a little bit curved. But let me go zoom out. So you see, this is the real graph. And then, first of all, is it possible? Do you see that there are two intersection points? Yes, that squares with these answers. At least GeoGebra gave me two exact answers. And let me do the same trick. I go here, if I want, I go to intersection, I highlight this one, and I will highlight that one, and I get these 2 points. So I have two answers, yes? One of them is this one, and the other one is this one. And then you can see some approximations here. So A is this point with, no, this is clearly that this is the point B. Yes, this one is B because this number is smaller and this number is bigger. So this is A. So this point is A, this point is B. If I ask you what are the approximate solutions of this equation, you would say this is 18.66 and the other one is 1.33. Yes, these are the approximate solutions. But the good news is that for quadratic equations, we can always find the exact answers. Okay? The exact answers. But for higher degree equations, it might be the case that this is the best that we can do. We can calculate the roots. Of course, for particular cases, we can find the exact answers. But for higher degree equations, usually we can find approximate answers. But the good point is that we can calculate them to any desired accuracy. Mathematics itself provides us with a means to calculate the roots up to any desired accuracy. Okay. By the way, there should be some way that we can approximate this number. So let me see if I calculate. Can I convince myself that this number is more or less the same thing? There should be an instruction. So let me see if approximate works or not. No. Approximate. Yeah, it doesn't work here, but let me numerical. I don't know. Numerical. No. So I can probably Google it a little bit so that approximate value GeoGebra. So let me see if I can see how it works. Alt click on it. Okay. Let me see. So let me write it here. So let me copy and paste this if possible. I don't know. Working with this GeoGebra is a little bit strange. Usually the easiest thing is to copy paste. Let me just be patient and write it down, okay? So I would say, for example, A is equal to minus 5 square root of 3 and then plus 10. Okay, it is working. You see, I just put this number in GeoGebra. This is the exact value. And then when you approximate this value, you get this number, which you see is exactly this number. Yes? So what we have done is completely correct. Okay, so you can solve all type of these questions. For example, let me just give you one higher degree equation. So let me clean everything here we had. Of course, this part is not part of your lesson, but I'm just telling you that if you know how to solve these problems using graphical tool, you can immediately solve higher degree equations. So for example, if I want to solve this equation, x to the 3 minus 3x and then plus 2 equals to 0. I want to solve this one equal to 0. This is a third degree equation. So I put y equals to this, and then I immediately get the graph of the function. If I zoom in a little bit and move it the other way around, so you see this is the third degree equation now. Yes, and this is also a coincidence. I accidentally gave you a good question. So how many solutions do you see? By the way, this is a third degree equation. According to the fundamental theorem of algebra, if you remember, I told you that the number of solutions is at most 3. But how many are there for this function here, according to the graph? Okay. 2.
Yes.
One of them is how much?
-2, and the other one is 1.
One is positive 1. Exactly.
Exactly.
So you see, now whenever you have this, any function, even the equation is complicated, but you understand how to solve it graphically, which is a very important thing to know, understand, okay?
Babak, I have a question.
Yes, please.
It seems that depending on which exponent you have, the general form of the graph stays the same. So all x to the power of 2 was like a u in shape, stretched out depending on what other variables you had, but still a u.
Again, this is not a general tool. For example, I can write you
No, but
this.
I was wondering why that is.
No, the reason is that because you need to know a little bit about derivatives, which is in Math 3C, to understand this behavior.
Okay.
Okay. But there are different. So I mean, this is not always the case. For example, if I draw this graph for you, this is also a third degree equation. Yes.
Yes.
But you see, the red one is this one. There is no U shape at all. So these topics are actually the topic of matrices. So the notion of derivatives, what you will go into study in next year and the next year, it is actually related to the being able to draw the graph of functions. So we want to understand these behaviors, why this third degree equation behaves like this, goes up and down, but why this, even though this one is also a third degree equation, a third degree function, it doesn't go up and down, it goes up all the time, but of course at some point it looks like a flat curve and then it still continues. So you see that the behavior of the red one and the green one are totally different, even though they are both of third degree. Okay, so the understanding of these behaviors is exactly what you will start learning from matrix C.
Oh, but
Okay.
Yes.
in the graph, how does a fourth degree equation look?
But again, there are different ways of them. For example, I can just draw 1/4 degree for you, which seems very similar. By the way, let us draw the famous quadratic one. It's good to know about these by heart. If I write y equals to x to the 2, so I don't know why this is still hanging over us. Okay, this is the function. So this is the famous function, quadratic function, the simplest possible quadratic function, x to the 2 without anything else. This is the graph of the function. But I can make it to the 4. It doesn't change that much. So the general form is the same, but of course this is the red one. It's a little bit more steeper, but the general form is different, is the same. But of course, this is not always the case. For example, if I don't know, I can just randomly draw a quadratic. I forgot the English name for that. The fourth power quitic, or so I don't know. I need to search. I have forgotten the word. Quitic is the 5th degree. Okay. So for example, I raise it to power 4, and then minus 3x to the 2. You see, suddenly these blue curves appear. So I have 2 minimum points and 1 maximum point here, of course, and these are. So you see, the understanding the graph of functions is actually the main topic of the calculus lesson, which you will start learning from next course. But you don't need to be worried about these things at all. What is very important to open GeoGebra, to play around a little bit with these things, to explore yourself. That would be quite fun if you like these things. Any questions?
No.
Okay, good. So let me just stop the video. Stop.